Good evening. I'm Bruce Campbell. I'm the chair of the Center for Earth and Planetary Studies here at the National Air and Space Museum. And tonight it's my pleasure to introduce the second of our Exploring Space lectures for this year. First of all, I'd like to thank our sponsors, Aerojet, Rocketdyne, and the United Launch Alliance. Please join me in thanking them for their support of this program. It's also my pleasure to introduce Scott Bolton, who you've already had a nice chance to Q&A with. Scott received his PhD in astrophysics from UC Berkeley, and since that time he's been a principal investigator on a number of different spaceflight experiments. He's been on a variety of different missions such as Magellan, Voyager, Galileo, Cassini, and of course now is the principal investigator of Juno. He's an associate vice president at the Southwest Research Institute in Texas. And tonight, obviously, he'll be telling us about the Juno mission to Jupiter. Please, again, join me in welcoming Scott.
Thank you, sir. Okay, so thanks for having me here. I'm going to talk to you a little bit about Juno and tell you what it's about. You can see the picture up on the screen. That's sort of a composite of what the new Jupiter really looks like. So you can see a little bit of the South Pole there, and it doesn't look anything like the Jupiter that we all grew up and knew and loved, which was, you can see a little bit of it with the zones and belts and the great red spot. The pole really does look a little bit more blue like that. I don't think we have a good understanding of what that is from yet. There's obviously some kind of chemistry, and there's a lot of storms under there. So you can see a picture of the Juno spacecraft there. It's a very, very large spacecraft, one of the largest that NASA's put together. This picture is not to scale. It's not as big as Jupiter, but it is very large. Each of those solar arrays are about 8.5 meters long apiece, so they're about 25 feet. And so the spacecraft goes through space cartwheeling, so it's spinning twice a minute. It goes all the way around, and it spans from sort of tip to tip about 70 to 80 feet altogether. And so it's a very, very large spacecraft and spins around. So what I'm going to do is I'm going to start off by kind of explaining why would we go to Jupiter in the first place? What was Juno really about? And then I'll go through and explain a little bit about the science behind it and how it works in its orbit, and then show you some current and recent results. Okay, so one of the first questions is how did our solar system get made? And that's sort of at the core of why Juno exists and why it was sent to Jupiter, is to understand the history and the origin of our solar system. And Jupiter holds a very special place in that history, in that it's the largest planet and probably formed first. And so the story that I'm going to sort of tell you starts before the solar system was formed. So we have a picture of maybe a galaxy. It doesn't look exactly like the galaxies that you might have seen. But nevertheless, lots of galaxies look like this. This is looks like the Milky Way, but on its side. And in these galaxies are tons and tons of stars, millions all across. Our galaxy is about 100,000 light years across. And embedded in these galaxies are clouds or nebulas. And they look a little bit like this. This is a Hubble image of a feature that's called the pillars of creation. And what these are dusty clouds. And what scientists have seen is that in the middle of these dusty, cloudy regions are young stars being born. And that's what this image up in the upper part of it, you see these young stars. It's very dusty. There's clouds. And these clouds are filled all through. They're not a lot unlike our clouds in our sky, except that they're almost all hydrogen and helium. They have a little tiny bit of all the other elements that we call the heavy elements. And in these regions, these stars collapse and stars are born. I'm sorry, in these regions, these clouds collapse and the stars are born from this. So what really happens is that we believe that, or scientists believe that there was a cloud residing where our solar system is now. It was there before our solar system existed. It collapsed, and our sun was born. And this cloud is spinning, so it has some angular momentum. And almost all of that cloud's materials, which are almost all hydrogen and helium, go in to form the sun. And then there's some leftovers left after you form our star. And those leftovers are spinning around, and they collapse down toward it to a disk. And so there's this dusty, cloudy material all around the young star. And most of that material goes into the first planet, which in our case is Jupiter. So Jupiter's more massive than all the other planets put together. I can take Saturn, Uranus, Neptune, all the planets, the comets, the asteroids, and they still don't add up to half of Jupiter. So Jupiter got most of the leftovers after the star was formed, our sun. Now the leftovers of the leftovers, that's actually us. It's sort of a humbling concept, but it's the truth. So after the Jupiter forms, there's more leftovers left because it only takes up some of them, and those go in to form all the other planets. Now Jupiter's so massive, scientists believe it must have formed first, because had it formed after other planets formed, it almost certainly would have disrupted their orbit and screwed up the solar system's dynamics. And so most scientists believe it had to have formed first. It also had to have formed early, because we see that it's almost all hydrogen and helium, just like the sun is. And that's what actually most of the universe of ordinary matter is, almost all hydrogen and helium. So Jupiter has to form while that hydrogen and helium is still around. Okay, so the history of our solar system, which is sort of what Juno's about, that's our main primary goal. And you see an artist's concept of the early solar system here, this black and white picture. You have the early sun. You're looking down on the solar system, so you're looking from above, looking down, and you see the early sun there in the center. Not the center, but the bright part on the left side. And then you have this dusty nebula cloud. Again, still mostly hydrogen and helium. And then the first planet forming out of that, causing a gap. Now, we have some telescopes now that can start to look out at these young places in other star systems. And we're starting to see gaps being formed like this. It almost looks like a record player. You know, if you're looking at a phonograph record from the side, or a CD, and you see these gaps getting created from planets possibly forming. So Jupiter is almost all hydrogen and helium, almost the same proportions as the sun. Saturn, Uranus, Neptune, they're all mostly hydrogen and helium. They change their exact percentages a little bit, but they all kind of lead us to have this consistent theory that these planets are formed from the leftovers after the sun. Except that we now know, and we've known for some time, that Jupiter is enriched in what we call heavy elements. So to a cosmologist, a heavy element is everything heavier than helium. So that's what I mean when I call it a heavy element. Now, if you talk to a geologist, a heavy element are the metals, the irons, right? They're talking about rocks. But to a cosmologist, everything beyond helium is a heavy element. So you've pretty much got hydrogen and helium, and then you got everything else. And if you look out in the universe, that sort of fits. Almost all of the universe of ordinary matter is hydrogen and helium. So how did Jupiter get enriched? We don't really know that. And it's a mystery. And back in the 80s and 90s, observations were being made of Jupiter that kind of gave hints that it had a larger percentage of some of these heavy elements than the sun had. And that puzzled scientists, and different theories were getting created to try to explain that. So we don't know exactly how or why that happened to Jupiter, but we know it's important, because the stuff that Jupiter has more of is what we're all made out of. So whatever process was going on in the very early solar system that allowed the Earth to get created and the elements that eventually led to life to come together started right away with the first planet. So the sun gets formed. Presumably its composition is the same as that primordial cloud that was out there. And then right away, the first planet starts to get an extra shot of these heavy elements. And eventually, the process must keep going so that you can eventually build an Earth, right? Which is almost all heavy elements. Now, we may have originally formed with more hydrogen and helium than we currently have, because if we did, we're not massive enough and we're closer to the sun, so the temperature's up, we would have lost all of our hydrogen. So if we had a big envelope around us, it would have escaped into space. But Jupiter's massive enough that it held on to it. So it's sort of this primitive object that we can go explore and get a hint as to what the early solar system was like. So different theories of how Jupiter got these heavy elements started to get created by different models and scientists. Okay, so just as a reminder, for those of you that don't remember your high school chemistry, this is the periodic table. It hasn't changed for a really long time. This is pretty much all the elements that we know of. At the top of that thing is the hydrogen and the helium, H and He, right? And then everything else is heavy. So on the far right-hand side, sort of that orange column, those are the noble gases. Those are special when we want to explore the solar system and understand our history, because they're called noble gases because they don't really react much. They don't do a lot of chemistry. So if you measure those, you kind of get an idea that what they were like originally. They're not changing a lot. They're not combining into complex molecules. And then there's other ones that you might be familiar with. The C is carbon, the N is nitrogen, the O is oxygen. You may have a favorite among these elements. My mom's favorite is gold. But the real message is, so Jupiter's got more of these heavy elements, and a lot of them are important, like the carbon, the nitrogen, the oxygen. They're sort of the root of organics, right? So not only do we make the Earth up, but we actually get the basics of life, right? So these are some of the things that we want to look for in the ocean worlds. We see some organics all over the place. The question is do they make the elements of life? They have to go a little bit further than just being there, but they probably are present in different places, and ocean worlds is a great place to look for them. So water, let me just point out that while hydrogen and helium are the most common elements in the universe, oxygen is the third most abundant element in the universe, and then probably carbon. So you have hydrogen, helium, and then oxygen. So water, which is two hydrogens and an oxygen, right, H2O, that's probably the most common multi-element molecule in the universe. And so water is very fundamental, not only to life as we know it, right? We believe water, at least on the Earth, everywhere there's water, there's life. So when we want to go look for life elsewhere, we look for the easy stuff, right? Look for water. Maybe we'll find life. But water's everywhere and very common. And so a lot of theories suggest that water ice must have formed very early in the solar system because oxygen was so abundant, and that played a role in the formation of the solar system. And the history of water is one of the big puzzles. We don't know how the Earth got its oceans. We don't know the real history of water in our solar system, and it may be very important to the formation and origin of life. So back in the 90s, NASA sent a spacecraft to Jupiter called Galileo. I was fortunate enough to work on it. This is an artist concept. On the Galileo spacecraft was a probe. So there was an orbiter, a spacecraft orbiter that sort of like Juno, wasn't designed like Juno, but it was going to go around Jupiter and study the moons and the magnetosphere and Jupiter itself. And then it had a probe that was released that went into Jupiter. And this is an artist concept of that probe falling through the clouds of Jupiter. and it had a heat shield that dropped off, and the probe went in, and its primary goal was to measure the enrichment. How much of each heavy element was there? Because we were trying to put together the puzzle of how you made a Jupiter. The first question is what's it made out of? What exactly is that enrichment? So here's a close-up, not an artist, but a real photograph of the Galileo probe. I love this picture because it's like watching a 1950s science fiction film. This is how it really looked. It's a submarine, right? But it's a submarine for Jupiter, which is a giant atmosphere, which is like a giant ocean. And this thing is just a submarine with a few portholes sticking out for the science instruments. And so this thing is the thing that dropped in and made the key measurements. So I'm going to show you a scientific chart of what those measurements were like. So the way you read this is at the bottom scale are the elements, the chemistry, right? So I have argon, krypton, and xenon. Those are some of those noble gases, right? They don't react with much, so we're going to go and look at those and see how much of those there are. And then you have carbon, nitrogen, sulfur, and oxygen. On the vertical scale is the ratio of how much the abundance of those elements relative to the sun. So if everything was 1, which is that horizontal line that's between light and dark is where 1 is, right? If everything lined up on 1, then it means that Jupiter was exactly the same composition as the sun. Now what you can see on that data is that none of them are at 1, but we knew that they were enriched. That's part of the reason that we sent it in there. We just didn't know if all of them were enriched and by how much. So what you can see is that almost all of them were measured, were enriched about the same factor, about 3 or 4. So it took about 30 minutes for this probe to drop down into Jupiter and make the measurements that you see before you. In that 30 minutes, every single theory of solar system formation was proven wrong. There wasn't a single theory that was left that worked. And I remember I was a young scientist. I was sitting in the audience when they showed this, and everybody went, uh-oh. Now, there's a couple of puzzles. Why is that? What went wrong? What was wrong with the theory? Or what's so puzzling about this? So I'm going to tell you there's 2 pieces to it. One is that all of them that were measured, and those are the white ones, ignore oxygen for now, just all the other ones are measured about a factor of 3 or 4. They're almost all identical. So each one of those elements was thought to have a different, well, isn't thought, but was known to have a different level of volatility. In other words, it froze at different temperatures, it gets trapped or between vapor and solid or liquid. They're all driven by different states of pressure and temperature. And so they should have been trapped or gone into Jupiter in different levels based on that difference in volatility. And yet they were all the same. And so what scientists thought is that they would see those measurements and they would be a little bit different from each other, and that would give them a clue as to how Jupiter formed. What temperature was it at? How far away was the sun? What was the early solar system like based on the difference in the volatility and how much of those each went in? The fact that they all got enriched by the same factor meant that the volatility didn't matter. So that means that Jupiter formed maybe where it was so cold that the volatility didn't count. It didn't make a difference. Or maybe it didn't form where it is now. I mean, no theory had Jupiter forming in such a cold environment. So that was the first puzzle. The second is that the majority of theories of how to enrich Jupiter were linked to water ice, which is represented by oxygen. The oxygen in Jupiter is tied up in the form of water. So the concept is that as the early solar system's protoplanetary nebula was expanding and cooling, water ice started to form and trapped these heavy elements. And then when Jupiter was made, not only did all the gas and dust get sucked in, but a bunch of dirty snowballs that were formed basically from water ice that had these other heavy elements trapped inside. Yet, the water that was measured was depleted. It's the lower yellow mark down there. And so the one thing that was supposed to be bringing in all the heavies, there was less of it. So that theory didn't work anymore. So that was the first puzzle. Now, scientists and theorists are very rigorous, but they're also very proud, and they try to figure out how to make things work. And so the first idea is we just got unlucky, and that Jupiter can't really have only that much water in it. It must be what we think, and that we just went into the Sahara Desert by chance of Jupiter. And there's some evidence for that. It was a little warmer in the one spot that we went into. We could see that from infrared telescopes from the ground. And so the idea is that we just went into the wrong place, and that if we'd gone in anywhere else, their theories would have been fine. And so everybody went away from that and said, well, we need to go back, and we need to go with a whole bunch of probes so we don't accidentally go in the wrong place. And we got to go really deep, because wherever we did, the water, we never got to where the water was. We could see the water was increasing right up until the time the Galileo probe stopped working. And the Galileo probe was designed to go to 20 bars pressure. 1 bar is our atmospheric pressure at sea level. So if you go to the ocean here and you're hanging out at the beach, you feel 1 bar of pressure. That's all the air kind of pushing down on us. It went to 20 bars, which should have been below the water clouds, but yet water was still increasing. So the idea is the water was lower. So we needed to go deeper, but that's an engineering challenge that we didn't know exactly how to do, and is very expensive. You saw the submarine already. That only went to 20 bars. Going to 100 bars means I need a much better submarine. So kind of went on the shelf, this whole idea, but we knew we had to go back to Jupiter to figure out the origin. That's where Juno came in. We started looking at ideas of how to do this that were triggered by Cassini. Actually, I was working on Cassini. We were flying by Jupiter on our way to Saturn when a couple scientists and myself got together, and we realized that we could formulate something like Juno and maybe measure the water remotely. And that's what part of Juno's main goals is, to go in and measure how much water is in Jupiter to resolve this mystery. And I'll go through that. I don't have the answer yet. It takes much more of the mission to get that number, but we're headed there, and we believe we got the right data. And what we do is we measure it remotely, and we measure it all over the planet. So I'll show you how that's done in a little bit. So the bottom line is that we're really looking for the recipe of solar systems. How do you make a solar system? So if you think of the solar system as a soup, and most of the people in here probably at least had some Campbell's soup at one point in your life, or some other canned soup. And maybe you tasted that soup as a kid and you said, oh, I like this. I think we ought to try to make some chicken soup. How would you go do that if you had this can? Well, the first thing you'd do is you'd turn the can around and you'd look at what was in the ingredient list. And you'd see chicken, noodles, carrots, some other vegetables, a bunch of things you can't pronounce, which is why you need to make it at home. But the bottom line is that the beginning of learning any recipe is looking at the ingredient list, right? And so that's where NASA is at. We're trying to understand the solar system formation. We're at the ingredient list. Juno is one step of that. We're getting the ingredients of one of the most important pieces, the first planet. But we'd like to get the ingredients of every object throughout the solar system, right? And sort of put it all together and understand, how do you make this soup? And what is the real process? So that's not the only thing that Juno does. That was our primary goal and the main push that we sort of thought of when we were first inventing the mission. But then we had this great orbit and a lot of science instruments, and so we not only look at the origin of Jupiter and the formation of it, but we learn about the interior structure, and this all folds into the origin as well. The atmosphere For the first time, we're able to see the deep atmosphere below the zones and belts and the beautiful pictures that you see. What's going on inside the planet? How do the dynamics really work? And then finally, the polar magnetosphere. We're going over the poles, so Jupiter orbits over the poles. All the previous spacecraft that have orbited Jupiter have gone around the equator. We're going to go over the North and South Pole over and over because we want to produce a map. And we also want to investigate what it's like inside. And so when we go over those poles, Jupiter has a magnetosphere like the Earth does, and that magnetosphere has aurora, or northern and southern lights. And in fact, you see here a picture from Hubble telescope of those aurora on Jupiter, and they're amazing. They're the most powerful aurora in the entire solar system. And in fact, not only do you have a little oval over the top and the bottom, I'm only showing you the north here, but what's unique about Jupiter's aurora is you can see spots that I have labeled here from the moons of Jupiter. So the 4 Galilean moons are the biggest moons of Jupiter, and those connect to Jupiter's atmosphere almost like an umbilical cord. They use the magnetic field like an umbilical cord, so the magnetic field of Jupiter comes out of Jupiter's poles, goes down around like a dipole magnet, goes around Jupiter and back in the other poles. And if the moons are in the right spot, that magnetic field threads right through the moons and back into Jupiter. And there are particles that are carried back and forth along that sort of umbilical cord that connects the mother planet to its moons and satellites. And what we can see is the particles coming off of those moons crashing into Jupiter's atmosphere, making it light up like aurora. And so that's what you see, these footprints. When people first discovered those, they didn't know what it was. And then they realized, oh my God, we're getting a trace as to where these moons are. So there are 2 main, besides doing all this science that we're going to, about the magnetosphere, the atmosphere, the interior, the origin has 2 main measurements that are going to discriminate among the theories of how Jupiter formed. One is the water abundance, which I'll get into a little bit more, but I already explained that a little bit. And the second is whether or not Jupiter has a core in the center of it. Now, it's a core of heavy elements. Surprise, that word comes up again. What that really means to most of us is there a rocky core in the middle. But what I want to make sure you realize is that in the middle of Jupiter, it's incredibly high pressure. And so the rocks in the center of Jupiter are not like the ones in your backyard. They are under an incredible amount of pressure. But if there's a core in the middle of Jupiter, that tells us something about what the solar system was like when Jupiter formed. Because one idea is Jupiter formed because rocky material started to get formed in the early solar system. They collected, and when they got collected, enough of them crashed into each other and stuck, that enough mass was there that it triggered the rest of the gas and dust to collapse onto Jupiter and form the planet. It could have alternatively just formed without a core, the way we think the sun formed. And nobody really knows whether it has a core or not. But you can't make the core of Jupiter after Jupiter's formed. Once I make this giant ball of gas, if an asteroid goes into Jupiter, it just burns up and evaporates in the atmosphere, like a meteorite does when it comes into our atmosphere. And it would just mix up into the molecular envelope rather than go collect into the bottom like it's sinking, because Jupiter's almost all gas. So those 2 measurements are the key to understanding the formation of Jupiter. What we're learning with Juno is that it's even more complicated than that, but fortunately we have the right instrumentation and the right orbits to do it. So how did we get there? So we launched in 2011 on August 5th out of Cape Canaveral down near Cape Kennedy on an Atlas V rocket. We were a very massive spacecraft because we have to survive the radiation of Jupiter. So we have 200 kilos of titanium protecting the sensitive electronics. So we're really big and heavy. And so we didn't have a big enough rocket to take us straight to Jupiter. So we went around the solar system. And the very creative engineers that figure out how to navigate around the solar system some time ago realized that they could do Earth flybys. And so we've done this on a number of different spacecraft. Galileo did it, Cassini did it, and Juno's done it, where you fly by the Earth and you gain speed by the fact that you go very close to Earth. You exchange momentum with Earth. So that happened in 2013, and then from there we went straight out to Jupiter. So the trick when you launch is that you're basically in orbit around the sun. You get away from the Earth, but you're just going around the sun now. And the whole trick is go fast enough to get far enough away from the sun so that one side of your orbit can reach all the way to the distance of Jupiter. And then with the help of a lot of clever engineers, the real trick is when you get out to the distance of Jupiter, you time it so Jupiter's there. I've been amazed at these engineers. I mean, I've studied this stuff, but I can't figure it out. But these are some of the most clever people NASA have working for them, is figuring out how to drive around the solar system. I'm really, really impressed with them. I can get to the store, but okay, so here's another picture of Juno. You can see there's quite a bit of science instruments on it. I'm not going to go through all of those, but we basically have a whole suite of instruments to measure the different kinds of energetic and charged particles in Jupiter's magnetosphere. We measure plasma waves, and we also measure the gravity field. The microwave looks into the atmosphere. We have cameras in the infrared, the ultraviolet, and the visible. And so they're all stationed looking mostly between the solar arrays. So as we cartwheel through space twice a minute, we look out between the solar arrays and can see Jupiter or wherever we're trying to observe. So there you see a couple of figures. On the end of one of those solar arrays, you see something that looks different, and that's called the magnetometer boom. It's basically an optical bench. It's very, very rigid. And on the end of that are two instruments that measure the magnetic field of Jupiter. And we put them way out there because we don't want to measure the magnetic field of the spacecraft. We want to measure the magnetic field of Jupiter. So we want to get away from the spacecraft. And located with them are 4 cameras that look at stars, so that if that solar array that may not be totally rigid flexes at all, we actually have a measure of exactly where that measurement is made, so that we can make very precise measurements of the magnetic field of Jupiter. So a very simple version of a magnetometer is what you go through getting on an airplane and TSA's checking to see if you have any metal, right? That's a magnetometer that they're checking with. Theirs is a little simpler than ours, but more or less the same kind of an idea, that you're measuring the magnetic field. Okay, so we go really close to Jupiter. There you see the ring around it is sort of the rings of Jupiter. We go inside of those. We do that because we want to make the measurements very precisely of the magnetic field and the gravity field, but we also have to avoid the radiation belts, which are just outside near those rings. And you can see a couple of moons around Jupiter that are close in there. So that we fly right over the poles. Those little tick marks are our tick marks. So we're flying really fast. It takes about 2 hours to go from the North Pole down to the South Pole. We're moving at about 250,000 kilometers an hour when we go by Jupiter, or 150,000 miles an hour. We're a little bit slower now that we've been there. The first one was faster. But we're really cooking to get through. And we do that because Jupiter's pulling us in, but at the same time, we've got to get in there, make the measurement before the radiation kills us, and then we just get out. So here's sort of what we've gone through 4 times, and this shows you the 4 orbits. We want to make a map, so each orbit is a different longitude, right? If I want to make a map of the Earth, I don't want to go over the same place, the United States, over and over again. I want to go over the US, Africa, I want to go over Asia. So we did first orbits, and we spread them out 90 degrees in longitude, so we have a very coarse map already. The idea is that after 32 orbits, we'll have a very fine map, so we'll understand the magnetic and gravity field and the atmosphere all over the whole planet. That's the key to accomplishing the objectives and learning not only how much water's in there, but whether there's a core and how the magnetic field really works in Jupiter. Okay, so one of the key things is this core, and I'm going to try to start a movie here. I think you'll recognize this guy.
We can learn about what's inside an apple by slicing it in half. We can learn a lot about what's inside a planet by slicing it in half. But they're planets. You can't really slice them in half. So how will the Juno spacecraft find out what's inside Jupiter. We don't know what's inside Jupiter. Jupiter could have a core made of heavy metal that's sunk to the center. Or it might be that Jupiter has this exotic material that's hydrogen squeezed down to such a high pressure that the hydrogen acts like a metal, metallic hydrogen. Now, we can't cut Jupiter in half. We don't have that capability. Instead, we have a happy little spacecraft in orbit around Jupiter. I'm a happy spacecraft orbiting a great big planet. Now, as it orbits, we strongly believe that there'll be slight variations in its path due to tiny variations in the gravity of Jupiter. And that will help us figure out what's inside. Now, how would we measure the tiny variations of the orbit of a spacecraft around a great big planet, millions of kilometers from here? Well, we would do it by measuring the frequency of radio waves. Radio waves coming from the spacecraft and radio waves coming from Earth. We can measure those variations like this, using the Doppler effect. Listen to the sound as the alarm clock moves toward you. Now listen to the sound as the alarm clock moves away. As it's moving towards you, the sound gets higher pitched. As it's moving away, the sound gets lower pitched. Now this effect, or this phenomenon, was described at first by a man named Christian Doppler. And to this day, my brother would like to have a rock and roll group called Christian Doppler and the Effects. But my brother's first name isn't Christian. So, we believe that by precisely measuring the path of Juno as it orbits Jupiter using the Doppler effect, we'll be able to determine from Jupiter's gravity the nature of what's inside. Is it heavy metal? Is it metallic hydrogen? Or is it rock? With the
Okay, so I couldn't have said it any better than Bill. So here you see an artist's concept of what the middle of Jupiter looks like. This was actually before Juno. This was constructed. In fact, we had it in the original design of the mission. And what you can see is that metallic hydrogen layer that Bill was talking about is that big orange area. So the top part is the atmosphere, and then you get to this region where it's so pressurized that the hydrogen starts to behave like a fluid, and it's actually conductive. It's believed somewhere in there is where the magnetic field gets created. And then if you go further down, maybe there's an ice rock core down at the bottom, and you can see that that's 40 megabars of pressure. So we can't make a piece of Jupiter on the Earth, right? We don't really understand how matter actually behaves at such high pressure. But with Juno's data, we can sort of unveil, is there a concentration of matter down in the middle or not? And we can learn something about even the equation of state, which we're slowly learning about as well. The top part on the right-hand side is sort of the meteorological layer, and we're sampling that through the microwave. So I'll go through that. So in many ways, what Juno is about is looking into Jupiter in every way that we know how. So one is the gravity field, which goes all the way down to the middle. The next is the magnetic field, which goes into the reddish zone. And then you have the microwave radiometry, which goes into the top part that's on the right-hand side. So we want to learn about the magnetic field because we don't know how it's created. We don't even know how Earth's is really created. We have a theory called the dynamo theory, but you can't learn much about it on the Earth because the Earth's crust has a permanent magnet on it. It's permanently magnetized crust, so we can't see in to where we believe the conductive fluids are creating the Earth's magnetic field. With Jupiter, it's transparent. So what I'm going to show you are some results now, and there's going to be a consistent theme that you hear from me, which is that, wow, that wasn't expected. And we're early enough in the mission that all we know is that we don't understand. We don't have a new answer yet. What we know is we have to rewrite the textbooks on how gas giants work and how giant planets and maybe the solar system formed. So we know enough to know we don't know. So here's one of the first passes of the magnetic field. So the lines in blue, what you see here are going across is time, and on the vertical scale is how strong the magnetic field is. The blue is what we expected from different models. They all kind of matched, and we expected to see that. The black is what really was measured. And what you see is that the peak is in the wrong place and much higher than we thought. So it may not seem that big of a difference, but this is a profound difference from the theory. What this means is that Jupiter's magnetic field has very high order terms in it. In other words, it has variability very close to the planet that nobody suspected, because it deviates from the model only really close to the planet. So from far away, our theories match perfectly. When you get close, they fall apart. We don't know why that is. One idea is that the magnetic field may be being created much closer to the surface than we thought. Also, the fact that this change is very sudden, only at closest approach, means that we need that fine grid of the magnetic field map, that map of the different longitudes, in order to sort out whether this continues or not. Now, this is only one flyby. Two of the other ones matched, and then the fourth one didn't again. So we're really puzzled. So that's one aspect. The next is I'm going to show you something about the core. So we measured the gravity field, and it also doesn't fit any theories. So on the left side, you see what people thought we might see. On the right side is a guess of what maybe is there. What we know now is that we don't think there's a real concentration of a core right in the center, but instead the core could be half the size of the planet, which is very hard to explain. And we're early that we may be being fooled by other things, but there's a possibility that Jupiter's core is very, very large and partway dissolved with the rest of the planet. We don't really know. Another way to look at this is that on this chart, you have, this is a chart showing J4 and J6. So what is J4 and J6? So J4 and J6 are a mathematical harmonic expression. So think of it as a game in math. So if I want to describe a guitar string plucking and it's vibrating, right, the music, I can write that out as a harmonic expansion in math, where I say this sine wave exists in this power and amplitude, and then the next one is another one, and each one will be a different frequency, and I can describe a piano string or a guitar string or almost any sound that way by just saying I have a sine wave of a certain frequency and I assign so much power to it, or loudness, right? So I can play a guitar string or chord, right? I'll have many frequencies being played at once. Some are louder than others, and I can write that out as an expression in math. So it turns out that nature works that way in lots of different parts of nature and in the universe. And one of them is I can describe the interior of Jupiter, both the gravity and the magnetic field, also with harmonic expressions, like it's resonating. I mean, Jupiter in many ways is ringing, and we're trying to figure out what frequency is it ringing at. There are many frequencies, and we use what's called spherical harmonics. So J4 and J6 are two of the amplitude terms in front of two different harmonic terms. So what it really means is that that's telling me something about how loud certain frequencies are, okay? You don't have to understand all the physics behind it, except to realize that the star, all the models are over there, and our data is in the right. And we don't know what that means, except to know that it's not, that our models weren't right. It's very puzzling. And what you're going to find, what we're finding is that the magnetic field, as well as the gravity field and the microwave deep atmosphere, are all puzzles, and that the whole inside of Jupiter is just strange. And there's something going on in there. And it could be that we're seeing asymmetries. People have always assumed that because Jupiter's rotating in 10 hours and it's really big and spinning, that everything must have all gotten mushed around and spread, and there's no rotational asymmetry, right? Everything is spinning like a top and has mixed together. And what we're seeing is maybe that's not true. There may be big blobs inside of Jupiter that are moving around. We don't really know. So somebody sent me a picture of a cake they made, and it looked remarkably like Jupiter. I was pretty impressed. I didn't get to taste this cake, but they obviously cut it open for a party, and they showed me that picture too. And I show this because I'm giving them some advice that if they go to make the cake again, I think their cake is wrong. And that they made the blue part thinking that was the metallic hydrogen, and that may be right, but instead of vanilla and chocolate in the middle, it may just be mocha. So we're waiting to figure out how to bake the cake. It's the recipe, right? We're after the recipe. Here's the microwave. So what you see on the thing that's wiggling is something called synchrotron radiation. That's relativistic electrons. And so you see Jupiter there and the magnetic field going around it, and the stuff that's red and yellow are really bright relativistic electrons that basically eat electronics. This is the reason Juno has to go so close to Jupiter, is to avoid those spots. So what we're doing is we're looking in the microwave, which is very sensitive to water. And the reason the microwaves, your microwave oven, is because microwaves interact with water molecules. So you stick a thing of wet spaghetti in your microwave and turn it on, and the microwaves come in and they heat up, or they excite the water molecules and heat up the spaghetti. If you put dry spaghetti, it won't work, right? So what we do is we fly 6 different microwaves, and each one sees down to a different level, because the high frequencies, the ones on the sort of the right side of that figure, they don't go very deep because they get absorbed by the water right away. The longer wavelengths, they can see even deeper because the water doesn't absorb them very much. And so we're watching the microwave radiation come out of Jupiter, and we're looking at it from many different frequencies at once, and we sort of invert the whole concept of the microwave oven to figure out how much water is in there. So imagine if I stuck some container of water that I didn't know how much it was in your microwave oven, but I knew the power of the oven exactly, and I knew how long it took before that water boiled. Then I could turn around after getting that experiment done and calculate exactly how much water you put in there, because I know how much power and energy went in, and I know how long it took to boil. So I kind of do that trick. It's a little more complicated than what I'm explaining, but I kind of flip the trick around by saying, okay, if I can see how much water is being absorbed by looking at all these frequencies, then I can get an idea how much water was in the way of the microwaves, and that tells me how much water is in Jupiter. And what you can see on this chart is that there's an ammonia cloud and then a water cloud. So the only other thing that's really absorbing microwaves in Jupiter is ammonia. So the first thing we do is we measure the ammonia. And we thought we understood that really well because the Galileo probe measured nitrogen, and we thought we knew how much ammonia was in there. So we thought, well, we'll do the easy part first, and then we'll go do the water. So here's the first microwave data. We got this from the very first pass. What you see is at the top is the channel that doesn't see very deep, and the bottom one is the channel that goes really deep. It goes several hundred bars of pressure. So on the bottom is latitude. So we go across the poles, right? So the equator's in the middle, and then you go plus or minus 40 or 60 degrees or so. And then on the other side is sort of the temperature or the pressure. Oh, there they are. Sorry for my noising here. So what you can see is we put a picture of Jupiter from the visible just so you could compare it. And so at the top, you can see that the squiggles from the microwave kind of match the zones and belts a little bit. And then as we go down, you can still see hints that the zones and belts are still present all the way at the bottom of the atmosphere. So that was the first puzzle, is we didn't think that zones and belts would go down that deep, but they do. This has been reproduced more or less from the other flybys, even though we go over different longitudes. There's some differences. But there are some strange things that come out of this, and another way to look at this data is through this plot. And what you're seeing here is on the left side is pressure, and on the, on the vertical scale is pressure, on the horizontal is latitude again, plus or minus 40 degrees latitude. And right away, the colors are how much ammonia there is. Now, we thought we understood ammonia, but this showed us that we don't. So there's a fountain of ammonia coming out of the equator. and we don't understand that. I wish I could tell you that we know what that means, but we don't. It's worse than that. Whatever goes up must come down, but we don't see where it's coming down. And Jupiter can't just be losing ammonia. So there's something very complicated going on with Jupiter. And the equator is very different from the middle and high latitudes. And we've now looked at the polar latitudes, and they're even so puzzling that I'm not even going to show it, because we really don't know what's going on here. But something's happening deep in that planet that is really mixing things around. And we're getting down to the levels where the ammonia is really rich down at the bottom. We didn't expect that. It could be that water's playing a role in this. We are just starting to look at the water. But it could be that this couples to the magnetic and the gravity field puzzles that we're seeing. Maybe everything is coupled. So while on Juno, everything is separated into different science teams and different working groups where people discuss science, we're now all meeting together because everybody's scratching their head saying, the answer must be in your data set. So we're rewriting the textbooks, basically, on giant planets, which is exciting. It's why you go. We knew it would be an exciting mission. I didn't know it would be this exciting. So here's one of the first maps we made of Jupiter in the infrared. So dark is a little bit cooler. Yellow and red are warmer, and you can see some of these storms are cool. They're sitting high up. When we went over the pole, we saw another puzzle. Here's the south pole of Jupiter in the infrared, and it's pretty bizarre looking. Here's the ultraviolet aurora. So this is the northern aurora, and up for the scale, I'm showing you Earth with its aurora, and we're pretty small compared to Jupiter's aurora, as you can see. This is some of the first time we've seen the whole aurora because normally from Hubble telescope, you're only looking, from the Earth, from the side, so you can't see the whole thing. We flew over the south. This was the first image of the southern aurora in the infrared, equally spectacular. Here's some data I'm going to play for you. This is from a thing called a plasma wave instrument. On the bottom is time, and on the vertical scale is frequency. It's kind of like flying a car radio. And we can take this data, and we can turn it into sound. So I'm going to let you hear it. The colors represent amplitude. So remember I was talking about the amplitude in front of those harmonic equations? In this case, the amplitude is like those, but it's just how loud, right? So yellow is louder than blue, and so you'll hear this sound. So it's pretty eerie sounding. There's an evil side of me and my household is that we decorate for Halloween in a pretty extreme way with a lot of motion detectors and different things like that. And this recording came down in August, and I said, let's use it. So my daughter would sit out at the window and say, oh, there goes another kid. They're running and they dropped their bag. We got another candy bag. So she didn't actually have to go out and trick or treat as much because we were scaring all the kids into dropping their candy bags. Here you see a picture. So we navigate around the planets, and almost all spacecraft do this with something called a star tracker. It looks out at stars, and it figures out where the spacecraft is pointing. This image was taken right near closest approach as we skimmed past Jupiter, and we looked out. The line going across the middle are actually the rings of Jupiter from the inside looking out. What you can see here is these are all the stars, which is what the star tracker is designed to measure, right? So the bright one just above the rings is Betelgeuse. You guys may recognize this if you're into astronomy. This is Orion. And you can see Orion's belt in the lower portion, the three bright stars. So in fact, if you're an astronomer and you go to Jupiter, the sky does look similar. This is proof that we are definitely part of the solar system, and the stars are all away from us. Okay, so we have a camera on board, and it's called Juno Cam, and we take all the images and we put them on a website. This is actually an old frame, but we take it on there, and amateurs or school children, anybody can go process their own picture of Jupiter and post it on our website. You can make any colors, you can do it any way you want. And in fact, we expanded it now. You can actually sign on and help decide where we point the camera. So there's a voting. You can propose you want to go take a picture of a feature of Jupiter. If whoever gets the most votes, that's where we point the camera. So this says it's coming, but it's already there and working. So if you go to missionjuno.com, you can find this website. I'm going to play a video for you that we did on approach to Jupiter, where we saw that we could see Jupiter and its moons as we approached on July 4th. And so for the 2 or 3 weeks as we approached, we took a picture of Jupiter every 15 minutes. And what you're going to see for the first time is the motion of the moons going around Jupiter. This is the first time that any human has seen really any motion of any celestial object. And so this is basically what Galileo saw when he pointed his camera. And it's put to music, and we sped it up to be like 3 minutes, so it's a lot easier than watching it for 3 weeks. But you'll see as we go through, Galileo looked up for the first time, and he saw that the stars around Jupiter seemed to change position each night. And from that, he realized that we were not the center, and that these things were going around Jupiter, and that Earth was not the center. He got into a lot of trouble. But here you see it. Innermost moon, Io, is going around in about a day and 3/4. Europa is the next one out. A few days it goes around. Then you have Ganymede and then Callisto. So they're all going around at different speeds. You'll see them blink on and off because they're going into the shadow of Jupiter. Getting a little bigger as we get closer and closer. So you can find that video on YouTube. So now I'm just going to show you a bunch of really cool images that we've taken. These are all made by the public and posted on our website. You can join this team. Here you see Jupiter looks like a painting. I'm just going to go through these kind of fast so you can just see the beauty of Jupiter. These are all processed from the raw data that we just post on our website. And the poles of Jupiter. Somebody took multiple pictures of the poles. Of course, when you go over the pole, it's always half lit because the sun is on the side, right? And they took multiple shots where it was always half lit and put them together to make one totally lit. So that's what the pole of Jupiter looks like. I think if anybody showed you that before Juno, nobody would recognize that as Jupiter. We would all think it was some other alien world that was very beautiful but made up by Hollywood. And some things are very artistic. People are expressing themselves, so I encourage you to go ahead and do that. You don't have to do just science. You can make your own cool pictures. Here's a little bit of how we took a couple of shots so you can see the motion and sort of see which way those cyclones are moving. So they're either cyclonic or anticyclonic. So I'm just giving you a sample of this. These are you can make these on your own. We didn't actually make these. We don't have the scientists doing this. Some people show the picture with relative to the Earth size. These cyclones that we see on Jupiter are pretty big. Some of them are very gorgeous. Some of them are very artistic. Here's one that's very artistic. Maybe that's the artist in the picture. I don't really know. And some of them just look like a Van Gogh painting. Or they just want to make it blue like the Earth. Some people took and put Juno spacecraft into it. Obviously, that we didn't take that picture. Or a purple one. And then one of my favorites is this one. I think Jeff Bezos would like that one. He wants to go fly there. And then maybe if you're on Europa and you look out, this is what it looks like. And someday maybe we'll be there. And then some people ask me if we have any passengers on board. So we don't, but we do have Lego minifigures. They're the next best thing. There's Galileo holding his telescope, and then Juno, the goddess, and Jupiter, the god himself. And then we have a plaque that commemorates Galileo's discoveries, which is very appropriate now that we just took the movie, which basically is what he would have seen in motion. So I think he would have appreciated seeing what he must have imagined. And there's the websites if you want to learn more about Juno. So I thank you. So I went a little long. Sorry about that.
Okay, so we'll go ahead and take some questions. I want to start up there.
Over here.
Yeah.
Just curious in regards to the cyclones and the red spot. You talk about is that a red spot and never seems to go away. If there's theories on why that is in regards to that being considered a storm, and obviously we have cyclones on this planet that go away. So anything that keeps that consistently there all the time.
So the question is about the great red spot, and is there any theories about how it is maintained? So there are different theories. I mean, it is considered just to be a giant storm. We don't actually understand it that well. We don't know what makes the color red, and we don't know why it lasts so long. What we see that it spins and blows around the planet. The good news is that on July 11th, Juno will fly right over the red spot for the first time, and so we're hoping to learn. One concept that is suggested is that because it's such a long-lived storm, maybe its roots are very, very deep. So you saw in the microwave data, you can kind of get an idea of how deep some of these zones and belts go, and the question will be is when we go over the red spot, does it show deeper roots than the rest of the planet, or are they all the same? And we don't know that, but we'll learn. Stay tuned for July 11th.
Could some of the interior lumpiness be a result of accretion of other bodies over eons of time? Because Jupiter would have attracted some other things like.
It could be. I mean, I think that most of the theories on Jupiter, I guess the question is could the interior motion that we suspect might be different than we thought be due to accretion or objects bombarding Jupiter and getting sucked in and sort of affecting things. Jupiter is really massive, and so we don't know of anything that big that could be hitting it. Most of the things like the comets that hit it at Shoemaker-Levy 9 years ago and things like that aren't thought to be massive enough to disturb anything like that. But maybe there are remnants. It causes something. You wouldn't think it would last this long, but anything's possible. It also could be possible that the core is dissolving, or there's just some sort of asymmetry that what we thought was rotationally symmetric, that nature just doesn't work that way. And this could be a hint that we don't understand giant objects in general. So most of the spacecraft, even ones that we've studied Saturn or flew by Uranus and Neptune, haven't gotten close enough with the right instrumentation to detect what we're seeing. Cassini is actually getting really close to Saturn, but it doesn't have all the instrumentation we have, but it may see hints as well. And so it'll be very curious to see that. Maybe Jupiter's more star-like. Maybe that's how stars work. We have to figure out how to get close to a star.
Far back, about 2/3 of the way back. Yes, sir.
Well, I think we'll make a progress figuring out Jupiter. I don't know if we'll be able to solve everything with just one mission. Usually you make your steps, you refine your models and questions and go back. His question was, what's next? What would I go study after Juno and figure out Jupiter? So I'm involved in the Europa mission already. So, you know, one of the things I'll be doing is going to study that. There's lots of other NASA missions that I'm involved with that either study the Earth or the Sun. And also, we're studying other future missions, maybe ones that go back to Enceladus. And I think someday, although I may be getting too old for it, that we would do a Juno-like mission to Saturn, Uranus, and Neptune so that we can sort of complete the inventory of these giant planets and understand how they all formed and how they work relative to the Earth. That's a long time to do those kind of things, and it took me a long time to get Juno, so I'm not sure. Maybe I'll see them started, but I don't know if I'll finish them. But I think that's the next question. And I think at the same time, extragalactic or extra solar studies, you know, how do giant planets and planets work in general around other stars is maybe a really big thing that's coming up now as well that I'm very interested in. He's picking them, not me.
I'm just curious, we're going to go back to Jupiter in another mission at some point, or any other part of the solar system. Is NASA working on any methods of space propulsion that are faster than what we have now? Are we seeing any progress there or something?
So the question is going there takes a long time. Are we working on any faster propulsion systems? So there are different systems out there. Most of them are slower than ours. I mean, what we use is chemical, right? I can use solar electric propulsion, which kind of spits out things. It's very good for low thrust. The real trick to getting out there faster is a bigger rocket. And NASA is working on that bigger rocket. It's called the SLS. And it's still being developed, but if that continues and gets developed and is able to get to the launch pad, that will allow very massive payloads or very fast travel, because the rocket can leave the Earth going at a faster speed. And that's really the trick. The other way to do it is to make the spacecraft very light, right? So New Horizons went out to Pluto. It took a long time to get out to Pluto. But they got past Jupiter really fast compared to Juno. They went on the same rocket that Juno had, but their spacecraft was like the weight of a paperclip compared to Juno. So they were able to get out there really fast, whereas we had to tolerate this incredible radiation, so we had all this mass, right? 200 kilos of titanium. So if you can make, and NASA is working on making small spacecraft, even CubeSats they call them. And if you can make an army of those, you can fly pretty fast too, and get out to targets. There's always challenges with each of these. If I make the spacecraft really small, it's hard to get enough solar power, solar area to collect energy to run it at Jupiter. So you kind of need a minimum size. But there's ways to do it. We're studying that. And you can keep making the spacecraft more efficient. So there's other ways besides just attacking it from a propulsion system.
Did you have a question? Yeah. How's Juno's health?
How's Juno's health? Juno's health is great. Everything is working, I'm really happy to say. We're in a 53-day orbit. Our original design was to go around in 2 weeks, 14-day orbits. And last October, we realized that there was something in the behavior of the rocket motor as we were getting ready to shrink our orbit. And so we decided to just stay in that orbit, because all the science, the same science, even a little bit better, could be done in the longer orbit. So it takes longer. You need a lot more patience, but you'll eventually get all the science and even a little bit more, because you'll study it longer, because we'll go around 32 times still, but it takes longer for each orbit. And you'll sample a little bit more of the space around Jupiter. So you actually get a little more. But we were lucky, because the same science that we were originally designed for could be done at 53-day orbits or 14. So everything is working great except for the rocket motor, but we don't really need it anymore. We have thrusters, so we can still steer and change our orbit a little. We just can't change a giant orbit change.
With the pressure and temperature inside Juno, is it possible that the probe is not reading how we would think it would read with the materials it's interacting with? Are there hypotheses on that?
Well, Juno is in space. So the question is I think, I'm not sure I understood the question. Your question is the fact that the pressure and temperature inside Juno affecting the measurements?
No. Is the pressure and temperature inside of Jupiter affecting the way that the instruments are reading? Could it be that the frequency and the wavelengths are changing based on something completely different we don't even know about?
Okay, now I understand. So if the pressure and temperature are very different inside Jupiter than we thought, then maybe some of the measurements are being affected by that. And that is very likely. In fact, that's what we're interrogating, is the pressure and temperature using this microwave instrument. They would not affect the gravity or the magnetic field measurement, but they might affect the microwave measurement. But in fact, the microwave is there to determine how the pressure temperature structure works. And so it could be that Jupiter's just funny, and that the way the atmosphere works and how much water is in there and how much but we pretty much understand the pressure because we understand the composition, as far as most of the composition. So the pressure is not something that you can dial a lot on. So I think what you're seeing is just that the deep atmosphere has a lot of dynamics in it that we didn't expect, and it's puzzling, and how ammonia and water are moving around in there are very different than what people had theorized. Now the question is how does that work and why? And the pressure and temperature is clearly a big piece of it. So you're on the right track. So the question is the fact that we're discovering giant planets around other stars, how does that connect to how we understand Jupiter and its formation? And they are definitely very connected. And when the Galileo probe first showed us all these puzzles and said, oh my gosh, everything was enriched the same, and maybe Jupiter formed where it was really cold. That was about the time when we were first detecting giant planets around other stars. And our earliest detections were based on measuring the wobble of a star as a giant planet went around it. So you could look at a star from far away and you could see that it wobbles. And that is because if there's a giant planet on one side, it pulls the star over a little bit, and it goes to the other side, it pulls it back, and you could watch that wobble. Now, of course, when you're doing that kind of astronomy, you're most sensitive to really, really big planets really close to their star. So that was the things we could observe first. And one of the first things that was observed was what they call hot Jupiters, giant planets at like the distance of Mercury. And that was a puzzle because theorists thought, well, they can't make giant planets that close to a star. And so it must have migrated there. Maybe it was moved there. It formed somewhere else and moved in. And then different theories started to be worked out, and there are different theories of planetary migration, and many people believe Jupiter's moved around. And so one idea was that Jupiter formed way out at the distance of Uranus and Neptune and then moved in. And that may be partly true. Or some kind of migration may have occurred in our early solar system. So they're all definitely coupled. And what we're learning about, what we learn about Jupiter and the formation of our solar system will inform us about solar systems in general and how they must form around other stars. And the reverse is also true. As we study enough of these other planets, we start to get an idea of how planets might be being made around other stars, and we look for ones that look like our solar system. We haven't found too many that look like our solar system yet. And it could be that you need Jupiter in order to form an Earth where it is, and we haven't seen a lot of that out there. But they definitely are coupled, and so we have astrophysicists that look at extrasolar planets on our team that are, sort of waiting to learn from us, and we're learning from them. And so in many ways, Juno represents scientists from across all the disciplines of NASA, the people that study the magnetosphere, the people that study astrophysics, as well as the people that study the solar system.
Well, please join me again in thanking the sponsors, United Launch Alliance and Aerojet Rocketdyne. Thank you for coming to tonight's presentation, and on May 2nd, we have the third in the series. Mike Brown will be here to talk about Planet 9 from outer space. And finally, let's again thank Scott Bolton for a terrific talk.
Thank you.